Okay, good afternoon, everyone. I'm very happy to be here. We are very happy to be here and honored to present you the review on OB associations. I am Eleonora Zari. I am a postdoc at the Max Planck Institute for Astronomy in Heidelberg, and I will give the first part of this talk. Then Marina Kounkel will give the second part. Marina is also a postdoc at Vanderbilt University in Tennessee. We are giving this talk on behalf of Nick Wright, who has led the writing of this chapter. Nick Wright sends his regards, apologizes for not being able to come, but he decided to follow the conference from the UK for environmental reasons. And also Simon Goodwin, who is here in the audience, and Rob Jeffries. Good. So let's start with the motivation. We have decided to write this review because in recent years it has become clear that most young stars are formed in large unbound groups that are called OB associations. So the topics that this review tries to cover is what are OB associations, how do they form, and finally how do they evolve and disperse in the field. And this is interesting because we can, by studying OB associations, we can try to have a broad and complete view of the process that regulates star formation, particularly when the environment plays a fundamental role. In particular, we know that massive stars emit wind, ionizing radiation, explode as supernova at the end of their life. And this has impacts on young star formation and the protoplanetary disks formation. Also, and we will talk about this more in the following of the talk, the environment, the density in OB associations is lower than the density in typical massive young cluster, and we know that the density in which stars form has an impact on, for example, multiplicity, binarity, and also, again, evolution of protoplanetary disks. Also, and this is very dear to my heart, OB associations and in general O and B type stars are bright and luminous, and therefore they can help trace galactic structure to farther distances. And this is done in the Milky Way, but of course also in other spiral galaxies. This is a plot that shows density distribution of OB stars in the galactic disk. Similar versions of these plots have been shown by João Alves in his talk. This plot shows the stars, not the dust, but the coordinates are exactly the same. So we have the x-axis points toward the galactic center, which is more or less here. The sun is at the center, and y goes towards galactic rotation. So here, this is the density of OMB stars. The region of low densities are color-coded in yellow and orange, and regions of high densities are these little blobs here in purple and black. And I have highlighted here a few of these overdensities because these overdensities correspond to OB associations that are relatively well studied, such as Cygnus, Cassiopeia, down here, for example, Carina. But you can also see in this plot that there are large-scale features, and these large-scale features correspond to what we think are fragments of spiral arms in our volume. Now, in the last, I would say, 5 years, there has been a lot of progress in understanding of our understanding of the properties and the nature of OB association, and this progress has come mainly from Gaia, and this review is basically only talking about results that are based on Gaia DR2 and following releases. So the outline of the talk is displayed in this slide. I will first talk about how we identify young stars and how we identify members of OB associations. Then we will review the properties. We will talk first about size and structure and kinematic properties of OB associations, and I will start by giving some conclusion on how associations are formed. And then Marina will take over and she will speak about ages and star formation and the propagation of star formation, the evolution and dispersal of OB associations. And finally, we will discuss some implications for binarity and protoplanetary disks if you are a star that is born in an OB association in contrast to a cluster, for example, to a dense cluster. And we will conclude with some future prospects. So let's start with the beginning. What are OB associations? In the review, we have proposed a definition which reads more or less like OB associations are groups of young stars. Their stellar density is lower than the density of the galactic field, and they are not strongly associated with interstellar matter. So there are two important caveats to these last 2 points. OB associations are extended in space, are very large structures. And even though they are not associated to interstellar matter, they can contain star-forming molecular clouds. As an example, this is a picture of Orion. All the bright blue stars in this figure belong to the Orion OB association, and me and Marina have spent a lot of time and effort trying to understand the structure of Orion. But as you know, in Orion, there is currently star formation going on in the Orion A and Orion B molecular clouds. And also, in Orion, there is the Orion Nebula Cluster. Of course, the density in the Orion Nebula Cluster is much higher than the density in the entire association. And both the cluster and the clouds are within the boundaries of the association, although they are not defined per se as associations. Whoops. Right, so how do I identify members of associations? So OB associations were called OB association because at first it was possible to identify only the brightest members of association. Using Orion as an example, here is a figure by Blau 1964 that shows O and B-type stars in the association. They are already divided in subgroups because astronomers like to divide things in subgroups. And these subgroups actually reflect physical properties. For example, in this case, the spatial extent. And D is the Orion Nebula Cluster. In this case, it was in the 60s, it was possible only to identify as I say, the O and B-type stars that were members of associations. In the 90s, it was possible to extend the classification, the identification of members to F-type stars. This is a figure adapted from Brown et al. 1994 that shows again the entire field of the Orion association. The orange dots correspond to the candidate members. And in this paper, Anthony Brown tried to relate the stellar content of the association to the structure of the gas. And you can see that some stars that belong to Orion are separated from the gas, while some others are still related to the Orion A and the Orion B molecular cloud. Now, the rest of there are several ways to identify low-mass members of OB association, and we're not going to mention them here. They rely on infrared luminosity, on X-ray activity. Here we just wanted to point out how to identify members using optical photometry. This is a color-mounted diagram of this field, a relatively small field, again in this region of Orion, showing the distribution of all stars towards the region by VII et al. 2014. And you see this sequence of luminous, low pre-main sequence stars standing above the field star population. So these pre-main sequence stars are young, low-mass stars. They are more luminous than main sequence stars with the same mass because their radii are larger because they're still going down the Hayashi track and contracting. And in the case of Orion, it was possible to identify in this way low-mass members of the association, but this technique was, before Gaia DR2, limited to a few associations and limited to the case where good photometry was available. Now, these changed dramatically after Gaia DR2 because Gaia provided distances to 2 billion sources. And with distances, you can compute absolute magnitudes that give you, I'm a observer, so I talk about absolute magnitudes as basically its luminosity. So it was possible for Orion, but also for several other associations, to construct color absolute magnitude diagrams. Here I'm showing all the sources towards Orion, and most of them are on the main sequence. A few are massive stars, and a few are low-mass young stars on the premier sequence. And it became, from the 25th of April 2018 onward, relatively easy to select all the population from high masses to low masses of OB association. As I said, not just Orion, but all the OB associations, at least in the solar neighborhood. And this is what the distribution of the sources in the sky look like. Here is a density plot. The background is, again, an extinction map showing the Orion A and the Orion B molecular clouds. Now, I have already hinted at it in the previous slides, but OB associations are, as I said, structures that are extremely large. They are several hundred parsec wide. And within single OB associations, one can find subgroups or subclusters in several star-forming regions. And as an example here, just to mention another association, we don't want to talk about Orion the entire talk, Cassiopeia OB6 can be divided in 3 star-forming regions, and then within star-forming regions, young star-forming clusters can be identified. So with Gaia, it was possible to study in detail OB associations in the solar neighborhood. Here are 2 figures showing the distribution of young stars in SCOSEN from Damiani et al. 2018 and in Orion from Kounkel et al. 2018. This plot shows the density distribution of the sources, and as you can see, there are several little clumps and groups in which the association can be divided. And instead here, Kounkel divided the association in 5 main subgroups. It is important, the most important part is that all these subgroups has different ages and different kinematic properties. And these gives us information about how star formation has progressed within the association, and how, in general, associations are formed and evolve. With Gaia, it was not only possible to study things in the sky, but also in 3D space. You have already seen this plot. This shows the density distribution of groups in SCOSEN. This plot shows these dots are all little groups in which the Orion association can be divided. Here, the points are color-coded by age, and the younger ages are in red, the older in blue. Here's the opposite, young is blue, and red is older. And instead, for Taurus, this plot shows a distribution of stars. Some of them are more diffuse, and some of them instead are a bit more clustered. And the main conclusion from these studies is that the density in a V association varies, and it can vary from 10 to the minus 3 stars per parsec cube in Taurus to 10 to the 3 stars per parsec cube in the Orion Nebula cluster. And the way this density can be is extrapolated, of course, changes depending also on the group that is studying the single OB association. So these are also somewhat sociological plots. Now, going to the kinematics, in the Hipparcos era, it was possible to study the kinematics only of the most massive members of associations. Here is a plot showing the distribution in the sky of the massive members of SCOSEN, and here the little arrows are the proper motions, so the velocities projected on the plane of the sky for members of SCOSEN. Before Gaia, it was not possible to really study in detail the kinematics of, for example, the internal kinematics of associations, but it was possible to anyway reach some interesting conclusions. All members of OB associations seem to move towards the same direction. they have a small velocity dispersion. And since the densities are low, it was possible to compute the virial state of associations, and in general, associations are found to be supervirial. Now, with Gaia, the R1, it was possible to study in detail the kinematics of the associations. In the case of SCOSEN, for example, this is the same plot, the same field as in the previous slide. This time, the proper motions are plotted subtracting the sun motion. And here you see that different groups of stars in the associations move towards different directions. For example, upper SCO move down here, and then this is lower Centaurus Crux move towards the upper right corner. And we see these kind of patterns, so different subgroups in the B associations move in different directions in all associations, and we usually refer to these as kinematic substructure. Not only it was possible to study broad motions, but it was also possible to study inner motions of subgroups within single associations. So in this work, Tristan Cantagoden and collaborators analyzed Vela, OB2, and divided the stellar population in several subgroups, again. Here, all the groups are color-coded in different colors, and then analyze the kinematics of the single subgroups. This is an example of the motions of the subgroup that's color-coded in orange. And as you can see, all these vectors, all the velocity vectors, are pointing outwards. And this is a signature of expansion. And our understanding is that almost all subgroups in OB associations are expanding, even if the entire association is not expanding as a whole. And this brings me already to the first conclusion, the first of this part of the talk. So we have studied the properties in terms of size, structure, and kinematics of OB associations. And we have found that associations form with a very similar spatial configuration as what we currently observe them. And this reflects the configuration observed in giant molecular clouds, both in terms of space and kinematics. So as an example here, we have a figure from Kounkel et al. 2010 that shows the density distribution of molecular hydrogen in Aquila. It's a giant molecular cloud, several tens of parsec wide. The cores that now I will highlight, yes, follow the distribution of the dense cloud, of the dense gas, through the entire extent of the cloud. And these cores will form stars, and after the gas will be dispersed, the stars will be shortly visible as OB associations. So now for the second part of the talk, I will give the word to Marina, who's gonna talk us about ages.
So, in order to understand the star forming history of these associations, it's important to be able to measure ages of all of the individual stars. And the way that it's traditionally done is through examining the photometry of all of these stars and placing them on the HR diagram, comparing their fluxes to the theoretically computed isochrons. Here is an example of this for two different regions. Here we're looking at only at the high mass stars. Here we're looking at the low mass stars. And in both of these cases, you need to be aware of certain caveats. For example, for the high mass stars generally, because you're looking at the tail of the MF, there wouldn't be as many of them. And because the evolution of the massive stars is so rapid, it wouldn't necessarily take many significant uncertainties in order to shift the ages significantly. On the low mass end, you certainly have many more stars, but you need to be very careful in how you treat photometry of all of them. For example, you need to be very careful in how you correct for the extinction, because that will shift everything significantly. And also, you need to be aware that, again, the evolution of all of these stars is fairly rapid. You do have an intrinsic age spread that you can actually observe. You don't have clearly defined cluster sequence for quite a while, but somewhere within this age spread, you also have binary stars. binary stars would be more luminous than single stars because you have two stars there. And if you don't take that multiplicity into account, you would infer younger ages for them than you would for the single stars. Still, this is by far the most widely used method for determining stellar ages. This is not the only method. Especially in the recent years, there have been several spectroscopically defined techniques out there. For example, lithium. Lithium is a very useful indicator because in low mass stars that are fully convective, lithium depletes very quickly as soon as the star contracts to small enough sizes to reach high enough temperatures. And as soon as a star reaches that critical temperature, lithium will deplete and you would no longer see it. So if you do observe lithium absorption, this guarantees you that the star is very young. And because the stars contract in a mostly regular way, you can build models of when you expect stars of a given mass to reach that critical temperature. You can look at the distribution of lithium in order to determine the ages of stars. Another very important indicator is H alpha. Now, most commonly, H alpha is used to separate out between the stars that are actively accreting, that still have protoplanetary disks, and the stars that no longer have protoplanetary disks. But H alpha is also a very important indicator for the magnetic activity. Magnetic activity of stars decreases as a function of age. And here you can see some of the preliminary results from the Sloan Digital Sky Survey when we look at the large census of stars, both young and old, on the low mass, and you can clearly separate out the sources that have been targeted as young from all the other much more evolved field stars. So by observing a large census of them, it will be possible to build a correlation of stellar ages through H alpha alone. And finally, there's also surface gravity. Surface gravity basically is a measurement of how large a star is. Historically, it has been somewhat difficult to use because it has been difficult to specifically calibrate H alpha to some sort of calibrate surface gravity to some sort of absolute scale. But with large surveys, it is becoming significantly more reasonable to do. And here you can see another early plot from a Sloan Digital Sky Survey. All of these sources are color-coded by the photometrically derived ages. And as you can see, they agree with ages derived from the surface gravity quite well. So being able to measure all of these ages, what can we actually tell? Well, even in a single subgroup, you can have a significant age spread. So if you were to take a small part of the OB association, it wouldn't be uncommon for it to be able to form stars for at least a couple of million years. And when you look at the entire region as a whole, you can have age spreads of several tens of millions of years. For example, here we have Orion, which we have looked at before quite well. Here, this part is by far the oldest in it. It has typical ages of around 12 million years, and it's no longer associated with molecular gas. But on the other hand, in the Orion A and in the Orion B molecular cloud, you still have molecular gas. You still are actively forming stars. So you do have something of a gradient from the older end towards the younger end. Similarly, in SCOSM, you have parts that are as old as 25 million years. You have parts that are as young as 5 million years. And you still also have a couple of isolated pockets of star formation there as well. So you do have this very large age gradient. All of these stars within LB associations are undoubtedly related. They stand out very clearly kinematically from all of the stars in the field. But it just takes certain portions of the cloud longer to collapse to be able to form stars than other parts of the cloud. It has long since been understood that massive stars play a significant role in shaping the star formation in these OB associations. Massive stars, they have H2 bubbles around them, produced either through photoionization or through supernovae, through winds, etc. And These H2 bubbles can eat into the molecular clouds, thereby destroying them. But on the interface between this H2 bubble and the molecular cloud, you can have you influence the formation of the next generations of stars. So this is a rather old image of it. You can certainly have something that is a bit more complex. For example, if you do have a filamentary molecular cloud, if you form a small subcluster in this region, it will be much easier for ionization to escape perpendicular to the filament than it is into the filament, and so that H2 region might come around and might push on the cloud elsewhere, and it's then the supernovae in that newly formed subcluster that are going to shape the star-forming history of the rest of it. So this has been the model that has been proposed to explain the star-forming history of the SCO-SEN. The supernovae and massive stars don't necessarily have to come from the association itself. They could come in from another region. For example, Vela. Vela is actually quite interesting because it's located in the galactic plane. There are several other OB associations in a similar volume of space that are unrelated to Vela, that are very, very different kinematically, and they have very different ages. And there's particularly one older region that has an age of around 30 million years. And the Vela OB2 association itself appears to be forming as a bubble around that older region. So it's probably the supernovae from that older region which have shaped and influenced the star-forming history of this region. And as Zhao has talked about before, Orion itself all seems to be expanding. It has an expansion age of around 6 million years. You can take all of these subgroups and project them back to a more or less the same starting point. So there have been a supernova or several that had influenced the formation of Orion, including enabling the formation of the Orion Nebula, the singularly most massive region in the solar neighborhood. And just like massive stars interact with the molecular clouds, massive stars also interact with with protoplanetary disks. Here you see an image of a young proplet that is located very close to massive OB stars in the Orion Nebula, and it is in process of having its disk being evaporated. Here you can also see Cygnus. Here all of these stars in black, they're located far away from massive stars. The stars in blue are located close to some of these most massive stars. And looking at this, the disk fraction of these stars as a function of how much UV radiation they're exposed to, you can see a definite trend that the closer a star is to a massive star, the less likely it is to have disks. And the further away, you still are able to maintain fairly high disk fraction. So this has profound implications on the eventual evolution of these stars, because protoplanetary disks is where planets are going to form. And so by destroying the disk quicker, you impose certain constraints into the planet formation as well. Not just protoplanetary disks. Environment also affects many other properties of stars, including multiplicity. For example, here you see a simulation of a young cluster. All the stars are orbiting around it, and it's not uncommon for certain stars to pass by other stars in close proximity. And if you do have a binary companion that is somewhat separated away from you by a few hundreds of AU, maybe a few thousands of AU, it wouldn't be uncommon to encounter another star at a significantly closer proximity than that binary companion. So these white binaries are not expected to be very stable in these dense clusters. And here you can see in the simulation, 2 stars are being ejected outwards from the cluster, most likely because they have originally originated in a binary system that has dissolved. Not all of these ejections are quite so energetic. Sometimes you might just gently separate out these stars, but these runaway stars are some of the most spectacular out there. And we see this in simulations. We certainly also see it in the real data as well. For example, here's the distribution of stars in the Orion Nebula separated out by the direction of motion. Here are all the stars that are moving towards the center of the ONC, and they form a shape of a very organized filament. On the other hand, looking at the distribution of all the stars that are moving away from the ONC, you have a much more spherical distribution of all these stars. You have a much greater range in the velocities of these stars. So again, most of these stars that are moving outwards most likely come from disrupted binaries. They inflate the overall velocity dispersion you do measure. Now, you might expect that density is the only thing that matters for the multiplicity. That in denser regions you should have lower multiplicity fraction because of these encounters. In more diffuse regions, you shouldn't have nearly as many of them, so you expect the overall multiplicity fraction to be lower, to be higher. But that's actually not necessarily what we see in all regions. For example, in the rest of Orion, if you remove the Orion Nebula, you actually see that there are more wide companions around the stars in densely populated regions than there are in the more diffuse populated regions, contrary to what you expect. And that could be because in denser regions, you are forming more stars, you have greater degree of turbulence in the first place. So what happens to all these populations after they get rid of their molecular gas? They persist together as a moving group because originally they had very small velocity dispersion. And with Gaia, in recent years, there have been several concentrated efforts in order to identify as many of these moving groups as possible, pushing down the age at which we're able to identify them further and further. And here you can see an example of just some of these young populations in the solar neighborhood, color-coded by age. Here we have Orion, Sco-Sen, and many other populations that do tend to have a rather filamentary structure that is representative of the molecular clouds from which they tend to form. And looking at them on the plane of the sky is one thing. It is particularly interesting to look at them in the velocity space as well, because you can see just how dynamic our solar neighborhood is, how all of these strings of stars get interwoven together. These groups are not bound. They are too large to be bound. They are dissolving over time. They're shedding the stars as they orbit around the galaxy. They are at the mercy of the tides. Here you can see an example of one fairly evolved structure, CR456. And right now, it has an observed size of all of the recovered members of around 190 parsecs. If you were to trace back all of these stars 60 million years, it used to be much smaller, at least for all of these stars. It used to be only 120 parsecs in diameter and around 50% smaller. But it's worth keeping in mind that even back then, it still had the same shape of a filament. That is to say, these populations, they are expand, but this expansion is somewhat organized. They don't explode every which way. They do persist as coherent entities because of their initial small velocity dispersion. So where do we go from there? Well, right now, the data that we are most dearly lacking are spectra. Spectra gives information on the radial velocities, which we need in order to better understand the internal dynamics of all these populations. Spectra also gives metallicity, it gives better spectroscopic ages, and many other things. And here you can see just all of the stars for which we have high resolution spectra available, at least all of the young stars. And it's fairly sparse. We have Orion, we have Upper Sco, Taurus and Perseus, just a couple of others, but really that's about it. And of course, there are spectra from Gaia, but I would highly advise you to avoid using Gaia's spectroscopic properties for the young stars. Gaia has obtained high resolution spectra of 30 million stars, but unfortunately, it didn't take into account some of the unique features that young stars tend to have, so those spectral parameters tend to be highly unreliable. But there are a number of other surveys that are obtaining spectra of all of these young stars. For example, as DSS5, I've already showed you some of the examples of the early science result that it's producing. It has been operating for about a year, and the first public data release is expected to be next year. Also here we have Foremost, which is expected to have its first light later this year. Here you see all of the stars that it's going to observe. And also there's there's various activity indicators, for example, X-rays that we can get with Eurozeta, and also variability, which traces spots, which also traces an indicator of age. So as we get more of these indicators, we will be able to push down the age of all the stars for which we are able to observe as members down to older and older ages without necessarily relying on the kinematics. So this brings us to our conclusions. So OB associations are an important region where stars are forming. They are representing the dominant mode of star formation in the solar neighborhood, not necessarily clusters. The words have meaning. When you say a word cluster, that brings a certain image to mind. So stars don't necessarily form in clusters, but they certainly do tend to form in these massive OB associations. And by understanding them, we are able to understand how stars form and evolve. And these large surveys certainly have exploded our understanding of them and will continue to do so. Thank you.
Thank you very much for this dual speaker presentation. Very comprehensive. Questions for Eleonora and Marina? Yes?
Hi, thank you for a really nice talk. I had a couple of questions, but let me just ask one for now. So I was really interested, so you have this 10 megayear spread that you find across certain associations, but then also tying that to the fact that the minute you have some OB stars, you can then irradiate these disks and irradiate these and create these proplyds and things. Do you see with that spread like a change in the masses with each kind of epoch of the stars? Like, are you getting more B stars for the later ones, implying that perhaps they can't accrete as much mass as the ages continue? Or I was just wondering if you could comment on that.
Yeah, sure. It's an excellent question. It's something that I think is still not very well understood, because measuring ages, it kind of depends on what isochrones you're using, and it can be somewhat difficult to match up the ages of the low mass stars and the high mass stars on the same scale to make sure that they are kind of forming at the same rate, because otherwise you would expect massive stars to form out later if you kind of assume uniform star formation rate and uniform inflow rate. So as we get better models, we would be able to address that question much better.
Cool, great. And just the other thing I was wondering about is, so you mentioned that with Gaia you're now able to resolve kinematic substructure across your OB associations, but you mentioned that multiplicity shouldn't be kind of dynamically disrupting things so much because these are much less dense and kind of different clusters. So what do you think is causing these kinematic substructures? Apologies if I missed it, but I was wondering if you could expand on that a little.
Yeah, I think it really depends on the kinematics of the gas where the stars are forming from. So we think that the kinematics of the star is inherited from the kinematics of the gas. And so depending on how the gas moves, then the stars will inherit the same kinematics property. And I have to say that I've shown things that are based on Gaia proper motions, not so much radial velocities. And so the proper motions are kind of independent from binarity. Radial velocities are. And it's going to be interesting to complement the Gaia information with all the spectroscopic surveys that are coming online in a few years that will give us much more information really in 3D.
Great, cool. Thank you very much.
Question on the other side?
Hi, thank you for the great review. I have a question relating to both the age gradient and multiplicity, and I was curious if it's possible for the binaries that do survive across these associations to look at if there are any trends in the binary properties as a function of age, in the sense of can you get some idea of a dynamical evolutionary history by tracing the age gradient and the, eccentricity or mass ratio or whatever binary property you're interested in?
Yeah, so this is limited by our ability to identify binary systems. And again, our ability to identify all of the stars in Orbi associations is still kind of very recent. So people have looked at binary stars in kind of classical star-forming region stars, or Orion Nebula, a couple of others. But we are kind of right at about entering the point where we are able to identify multiple stars across much larger scales. So I don't think we have the answer for that yet.
Thank you.
Yes?
Hi, Marina. Hi, Marina. Thanks for the great talk. I really appreciate it. Just thought I'd talk about your binarity discussion regarding the fact that seem to see a bit of an inversion of the binarity rates between the core of Orion and the surrounding regions compared to what we'd expect. I'm wondering as to what effect the ages of those regions might have on that, because I know that the central regions of Orion tend to be the younger components, and you might have a little bit of more time for things to disrupt and come apart for the less dense, more diffuse outer regions. So I'm wondering if you've got any sort of positions on, whether we have any, sort of age normalized data sets for looking at this sort of feature, and what might be necessary to better ascertain that. Thank you.
The specific conclusions were done in Orion Nebula clouds, excluding the very center of the Orion Nebula. So you don't really expect a significant age trends in there in comparison to the rest of the Orion as a whole. We've also tried to separating out the stars that clearly have portable interior disks from the stars from younger protostars. So we don't necessarily see any trends there as a function of disk presence. Not necessarily. We haven't looked at the age directly.
Very interesting. Thank you.
I think there is a question over there.
Yes, hi, thank you for the excellent talk. Could you help me understand why subgroups are expanding in those OB associations, and how is it possible that the OB association itself is not expanding?
Thank you for no, okay, so they are, we think that the subgroups are not gravitationally bound, and that's why we see expansion. And classically, the picture of the formation of OB association is that OB associations as a whole come from clusters that are dispersing in the field. Now we are revisiting this picture, and so what we are saying is that no, OB associations don't come from a single cluster, massive cluster, but there is a lot of substructure within these associations. And so what we thought it was expansion was as associations as a whole are actually the single little groups expanding in the field because they are indeed unbound.
But they were bound initially?
No. Very few of them are bound. For example, Orion Nebula probably is bound. There have been a lot of debate over it over the course of years, but it's probably bound. I think all of the other populations in the solar neighborhood are most likely unbound. But in addition to just gradual expansion, sometimes you might have something a bit more violent as well. For example, if you have a supernovae triggered star formation, you might see more organized expansion as well.
Okay, thank you very much.
Doug?
Yeah, so let's go from the small scale up to the bigger scale. You've got a whole bunch of these beautiful OB associations. What do you see in the random velocity of each association compared to the sort of just rotation around the galaxy? I guess I'm wondering about whether this tells us we can use that to try to get back to sort of with the formation, how much is this coming from supernova, sweep up, et cetera. So am I right that the first thing you see is just that these things are going around the galaxy almost on circular orbits and just spreading out? And how well can you get to looking at, let's say, angular momentum as a function of distance and see how much they've been perturbed?
Yeah, so here you can see kind of, this is just one of those few components. You can see similar things in the other two. For the most part, it is depends on their rotational velocity. You do have some peculiar velocity as well. They might interact with each other gravitationally as well to perturb each other. But yeah, so stars inherit the velocities of the gas. They tend to have very small velocity dispersion. So it tends to be fairly small, fairly organized.
Yeah, I think that velocity dispersion from OB association to OB association and compared with the circular might actually be an interesting diagnostic.
If I can also comment something else, to compute, for example, angular momentum, it's very important to use radial velocities. And at the moment, there is not much observational data, but that's going to change soon.
I have a question myself. I noticed that you included torus in your list of OB associations. To me, torus is more a T association. So my question is, in your mind, is there a fundamental difference between T association and OB associations?
No, I would say that it's all an association. OB associations are just named OB because there are OB stars, but there are stars in the entire range of masses, even to lower masses. It's just, so I guess it's just it's just associations. We could call them all of them associations without focusing too much on the high mass stars.
Yeah, and terminologies particularly became much more uncertain in the age of Gaia. Right now, there isn't a clear definition of what is a cluster, what is an association, so it's just easier to group all of the like things together, and just how many massive stars you have is not really an indicator of the similarity.
So maybe one way to reconcile Joao and Mark is to say that most stars form in association.
Yeah, no, I think...
OB or T or whatever.
Yeah, I think the four of us are not disagreeing. I think we're all saying the same thing, but we're just using different language. And I just, again, to me personally, the word cluster invokes a certain imagery that if you can try to convey it to other people, they would also tend to have particular imagery that they bring to this information that you may not necessarily mean. So
Or that we are right.
Maybe a final question from Thomas?
Yeah, actually, I have a related statement. You said the same. I actually disagree. And the reason is a very simple one. If you want to talk about feedback mechanisms, you need to have the massive stars. So there is a big difference, actually, between the two.
Sure, and in that respect, I mean, all of these regions have a very unique star-forming history. They have unique initial distribution of gas. You have different velocity patterns. You have different quantity of massive stars. So yeah, certainly, if you do have massive stars, that affects your environment. That affects the later evolution of the stars as well.
We may have time for a final question, if there is one.
One comment concerning the expansion of the subgroups. I think these subgroups mostly form in very dense cores, for which the potential of the gas is relevant, while the whole association has a much shallower potential. So while the gas is being expelled, this triggers the expansion of the stars in the subgroups, while the association as a whole is basically more or less confined, because that's not so much of a problem then.
Inside the region itself, you do have excess energy from various events, from disrupting multiple systems, from supernovae, from other sort of feedback. But, for example, in Orion, it's actually quite an interesting region because the entire Orion shows this very strong expansion. But if you were to take a look at all of the other smaller regions around it that haven't been affected by the energy ejection from the past supernovae, they all appear to actually moving towards Orion. So there is, within each region, you do have a very complicated history, but when you look at all the regions outside of it, you might actually be able to better trace out the potential of the region.
Thanks.
Okay, I think we are going to stop here. But if you have further questions, you can ask other questions in Mattermost. So the discussion is not completely over. And we are going to thank again Marina and Eleonora.